We've now looked at a number of different bifurcations, and we understand them quite well, at least on this level. But they're all, the equations we looked at were just sort of like toy equations. We just started with a single ODE, and we showed that they can have these bifurcations. And I told you that later on we'll see that these equations will be emerging from more complex equations. And we'll get there. But let me now just show you a couple of examples that exhibit the behavior described by these bifurcations, by these simple equations. And these systems are quite non-trivial. So let's look at a couple of examples. Now, one example you're very familiar with is like if you take a cardboard and bend it like this and you put a weight on top, or if you rather think of a more fancy version, you take a steel beam and have it curved, and it's called a bridge. And then the question is, how much weight can it support? And so if I draw that, okay, so here's our cardboard or our bridge, and we put a weight on top. And then the question is, what will happen? And so we would get a bifurcation diagram where if we plot here, we plot the weight, and here we plot the deformation. And so then as you increase the weight, the deformation will get larger and larger. And at some point, when the weight is too large, it will just snap through. And that snap through is a saddle node bifurcation, because what you have is, it looks like that, and then actually it merges with an unstable solution on the other side. But for this weight, then the deformation just becomes very large. And within this framework here, we don't know where it goes. In reality, then hopefully it will just go down to a state like this. But of course, that could also break, and who knows what. Anyway, so that's a very a real system which shows a saddle node bifurcation, as you sort of knew. So let's look at some other systems. A classic system that has been studied a lot in the 80s, 90s, last century, well, so a while back, I guess, were various fluid systems. And the reason people looked at those in great detail is because they were very easily controlled. I should say easily. One could very well control them. Someone could make precise experiments, and someone can test these bifurcation ideas in realistic systems with quite some precision. So one of those systems is the Tailor vortex flow, which is the flow between two concentric cylinders. So let me just sketch that here. So we have two cylinders. And there's a fluid in between. And so there's fluid in between. And when the inner cylinder rotates, then the fluid rotates around, and centrifugal force pushes the fluid out. But other places, the fluid has to come in again. And so it generates these vortices. And in this case here, you see a system which has is a very short cylinder. So you see here just two vortices. There's one vortex like that, and one vortex like that. Okay, so now in this experiment, what they did is they increased the rotation rate. And so the rotation rate is here is this epsilon, essentially. And they observed that as they increased the rotation rate, there was transition from the symmetric configuration. And so what they plotted here is the symmetry, the degree to which this vortex configuration is symmetric. And so it was symmetric for low rotation rates. And then for high rotation rates, it became asymmetric. And that's what you see on the right side. There's one big vortex. There's this big vortex. And there's a little vortex like that. And so you had the symmetry breaking. And that also occurred via a saddle node bifurcation, which you see here. So it went here, and then it jumped up there. And then if you then reduce the rotation rate again, it followed here and jumped down here. So you had hysteresis, where the jump from the symmetric to the asymmetric state occurred at a different value of the rotation rate than the jump back. Actually, I want to point out here that the system has more features yet. You see there's another saddle node bifurcation here, and which is where it jumps to the oppositely oriented state, which would be a small vortex here and a big vortex like that. I'll get back to that later, But let's first sort of just appreciate that here we clearly see in this fluid flow system, we see clearly three satellite bifurcations pop up. Okay, let's see what other systems are there where one sees satellite bifurcations. So this is a much more recent experiment, which is a little bit far-fetched maybe, but I thought it was quite interesting. So what they did here is they built a four-legged robot, and they, and I can't tell you what the details are, how they did that, but what they investigated is how the gait of that four-legged robot changes with the speed at which it goes. And they compared that with what happens with animals, like, you know, in a dog or other animals at low speeds, the gait is different. You know, the animal just walks, whereas at higher speeds, it goes in a trot, and at yet higher speed, it may go into a gallop. So there are these different gaits. And the thing I just want to point out here is the following: is excuse me. You hear the experiments in their robot, and as they increase the locomotion speed, they get a jump from this walking motion to the trot, which is a different gait. And as they reduce the walking speed, again, they get a transition back from trot to walk. But again, you have it at a different value of the speed. So you can have hysteresis. And they did measurements in dogs, which of course are much more noisy than the robot. But you also see, at least with some goodwill, you see that you have transition to trot at higher speed than the transition back to walk. Right? So you also have this hysteresis with a lot of noise in this case. So that's satellite bifurcations. So we also had a transcritical bifurcation. So this occurs in a number of systems. Here it shows up in what looks like a complicated case at first sight, but one can understand it, and let me guide you through it to some extent. So here, this is a convection, Rayleigh-Benard convection, which is, you know, you have a fluid layer and you heat it from below, so the temperature is higher on the bottom. And so therefore the fluid expands and it wants to rise. And sort of similar to the Tailor vortex flow, the fluid can't just rise everywhere, it has to come down someplace else. And again, so you get these convection rolls, which are similar to these vortices in the Tailor vortex flow that I mentioned. And if you now do a top view of such a system, then you can have different patterns. Now you could either have, you could imagine these would be just stripes. So you have just straight, you know, that it doesn't, it's just patterns like this. But in this case, what they find instead is actually these hexagonal patterns. So here you see this hexagonal pattern where the fluid flow, there's a top view where the fluid flow is up, where it's, the fluid is hot. And that's in this visualization technique, that's the black parts. And where the fluid sinks, it's cold, and that's where the white part. And so interestingly, you see here actually in this pattern that the fluid pattern is not everywhere the same. You have like no flow here, and you have these hexagonal patterns here. So what's going on here? So they did measure things that would generate a bifurcation diagram, which in this case is essentially the heat flux across the layer. So the stronger the flow, the stronger the heat flux, because the heat is transported by the fluid as it's moving around. And so as they measure the heat flux, which is measured here, they can see a bifurcation diagram. So look first here in this zoomed version. So that's zoomed in from around 0. And there you see a transcritical bifurcation, you know, like this. There's a transcritical bifurcation, which then there's again a satellite bifurcation, and then there's this other branch up there. And so this branch here corresponds to these hexagon patterns, and this branch here corresponds to the no pattern, or no fluid flow. When you see there is a regime of bistability between the two, because here the convective flow, the situation without the fluid flow is linearly stable, and the pattern is also linearly stable. And so here, that's why you can have both of these guys coexist in the same system, because there's really bistability. I should mention that this is a more complicated situation. You may have noticed that I just drew here this part, although there was nothing in the experiment. And well, one reason there's nothing in experiment because they plot the heat flux, which is not going to be negative. But the main point is that this whole system is described by a more complicated set of equations, which exhibits the transcritical bifurcation, but additional things. And in that more complicated state, this guy here, which in the normal transcritical bifurcation would be stable, is actually not stable. But that's something we'll get to, in a few weeks. We can talk about that. But I just want to point out here, so you have a transcritical bifurcation, which is connected with a saddle node bifurcation and then generates these stable hexagons in a bistable situation. Let me just mention in passing, there's in addition then a transition from these hexagonal patterns here to roll patterns here or stripe patterns, which, that's can be described in bifurcation equations as well, but that's, again, more complicated. Okay, so let's go further one more. So here's another system, which is also a fluid flow system, as indicated here, but it's not driven by heat or not by rotation. It's driven by electric field. It's a little bit complicated, but so let me not get into the physics of it. It's a liquid crystal, and the electric field, AC electric field, drives a fluid flow. And what they measure here is similar, this bifurcation diagram here, and they measure sort of the equivalent of what would have been the heat flux in the other case, but they measure the heat flux squared. And so, remember, if we have a pitchfork bifurcation, then it looks like this. But if you measure the square, then of course the square root becomes a linear function. And so that's what's actually plotted here for different conditions. And so that you see that for some conditions, that slope is relatively small. And as you change the electric conductivity of the liquid crystal, the slope becomes larger. And you see that it sort of has the trend to become vertical. Well, it's not vertical, getting vertical here, but you can see how this could become where the slope here would be negative. And so the bifurcation would go from a supercritical pitchfork to a subcritical pitchfork bifurcation. And where the slope is vertical, that would be our weekly subcritical case that we discussed, where the analysis with the quintic pitchfork equation would actually be valid. Having mentioned the pitchfork bifurcation, let me go back to that Tailor vortex system that we looked at earlier, which was more complicated than just a saddle node. And let's look at this more carefully. This system is formally, in theory, is actually reflection symmetric around this axis. And so this vortex should be the same size as this vortex. It should be really reflection symmetric. If that's the case, then what you would expect that if you get a transition from the symmetric to the asymmetric case, that should be a pitchfork bifurcation, a symmetry breaking bifurcation. And indeed, if you look at it a little bit further away from epsilon equals 0, indeed, you see that you have both positive as well as negative asymmetry, and this symmetrically related. But near the bifurcation point here, that's actually not the case. And so this is one of those situations where the system is not perfectly reflection symmetric, but rather there's a slight symmetry breaking, which is not intentional. It's just an imperfection in experiment, which leads to the fact that the basic state here, the symmetric state, which becomes unstable at epsilon equals 0, well, actually, because of this imperfection, it doesn't even exist anymore. And instead, you get this deformation of the pitchfork bifurcation into two saddle node bifurcations and another one here. In the ideal case, in the perfect case, the bifurcation would have looked like this. Let me draw that. It would actually have looked like that. It's a subcritical bifurcation, so it should have looked like that. And it's, let me try it again. This is what it would have looked like if there had been no imperfection. And the imperfection broke this point here and made it into a smooth curve like that, and a smooth curve like that. Somewhat similar to our discussion of the transcritical bifurcation when you break the condition that the solution exists for all values of mu. Okay, so you see that these these discussions that we had in these very simple systems actually show up in real systems. And so it is should be a good motivation to then look at how we obtain these simple equations from real physical equations that are more realistic than our toys. Okay, so much for that.